When you asked an AI something this morning, a building the size of 6 football fields, somewhere in Virginia, pulled enough electricity to power a small city. Not for a second, not for a minute, continuously, around the clock, every single day. There's a stretch of road in Loudoun County, Virginia, about 30 miles outside Washington, D.C., that locals call Data Center Alley. It does not look like much from the outside. Long, windowless buildings behind chain-link fences, cooling towers humming in the parking lots, tractor-trailer-sized diesel generators lined up along the walls like sentries waiting for something to go wrong. But behind those walls sits 199 data centers, more than anywhere else on Earth, consuming 4,140 megatwatts of power. That is more than twice the electricity used by the second largest data center market in the world, which is Beijing, and they are running out of room. In March 2025, Loudoun County's Board of Supervisors voted 7-2 to end all automatic approval for new data center construction. For the first time in 15 years, developers who want to build in Loudoun County have to ask permission, because the grid simply cannot keep up with what is being demanded of it. Virginia's power demand could rise by 183% by 2040. A senior official from one of the regional electric cooperatives said publicly that he believes the state will experience rolling blackouts before this gets resolved. This is not a software problem. This is a physical one. And to understand why, you need to understand what is actually happening inside these buildings. Because a data center is not a server farm, the way most people picture it. It is one of the most precisely engineered facilities ever built, designed to do one thing above all others: never go offline. Every major data center is built around 4 things. It needs land, ideally flat and cheap, with room to expand. It needs fiber optic cables, multiple redundant lines running underground that connect it to the broader internet. It needs electricity, enormous amounts of it delivered reliably from the grid. And it needs water to manage the heat that all of that computing generates. Northern Virginia had all 4. The federal government's presence there in the early internet era meant dense fiber infrastructure already existed underground. Dominion Energy offered some of the lowest electricity rates on the East Coast. Land was available and relatively cheap in the early 2000s. And unlike the desert Southwest, there was water, so companies built there. Then more companies built there. Then the cloud boom happened and the AI boom after that. And what started as a practical infrastructure choice became a geographic monopoly that the rest of the world now depends on. Northern Virginia currently handles 13% of all reported data center capacity on Earth, 25% of the Americas. A significant portion of every internet request you make today passes through those windowless buildings off Route 7 in Ashburn. Now let's go inside one. A hyperscale data center, the kind built by Amazon, Google, or Microsoft, typically draws somewhere between 100 and 300 megawatts of power at full load. A single facility at 100 megawatts is pulling as much electricity as roughly 80,000 homes. That power does not just flow straight from the grid into the servers. It goes through several layers of infrastructure designed to protect the equipment from any interruption, however brief. The first thing power hits when it enters a data center is a series of transformers that step voltage down from the high voltage transmission lines outside to something the building can use. From there, it flows into switchgear, which is essentially the traffic system for electricity inside the facility, routing power to different parts of the building and allowing sections to be isolated if something fails. Before power reaches the actual servers, it passes through what is called a UPS system, an uninterruptible power supply. This is a bank of large batteries, usually lithium-ion or lead-acid, that sit between the grid and the computing equipment. If grid power flickers for even a fraction of a second, the batteries take over instantly, so fast that the servers never notice the interruption. But batteries only last minutes. They are a bridge, not a solution. For longer outages, data centers run on backup diesel generators. In Loudoun County alone, the data center industry holds permits for more than 4,000 diesel generators, with a combined capacity exceeding 11 gigawatts. That is more than Dominion Energy's entire natural gas fleet. If a major regional power failure hit Northern Virginia and every generator in every data center spun up at once, the air quality impact alone would be significant enough that regulators have specifically flagged it as a concern. This level of redundancy is not paranoia. It is the industry standard. Serious data centers are built on what engineers call an N+1 or 2N model. N represents the amount of infrastructure you need to run at full capacity. N+1 means you have one extra unit of everything, so any single component can fail without the facility going offline. 2. N means you have a complete duplicate of every critical system, running in parallel, so that even during planned maintenance, you can take an entire half of the power infrastructure offline and keep running without interruption. Tier 4 data centers, the most resilient classification, guarantee 99.995% uptime. That works out to less than 26 minutes of downtime per year across all planned and unplanned outages combined. Power is the first engineering problem. Cooling is the one that keeps data center operators up at night. Every watt of electricity that flows into a chip comes out the other side as heat. In a conventional office server, that is manageable. A standard server rack draws somewhere between 5 and 10 kilowatts. You can cool that with air, the same way you cool a room. But an AI data center is not using conventional servers. The chip at the center of modern AI computing is the GPU, a graphics processing unit. Originally designed to render video game graphics, but repurposed over the last decade for the parallel processing that machine learning requires. The NVIDIA H100, the chip that powered the first wave of large AI models, draws 700 watts per unit. A single server with 8 of them draws over 10 kilowatts on its own. A rack of AI servers can draw anywhere from 60 to 130 kilowatts, compared to the 5 to 10 kilowatts of a standard rack. NVIDIA's newest Blackwell architecture pushes a full rack to 120 kilowatts or more. You cannot cool 120 kilowatts with fans and air conditioning. The physics simply do not support it. So the industry is moving fast toward liquid cooling, and it is doing it in several different ways. The most common approach right now is called direct-to-chip cooling. Instead of blowing cold air across the outside of a server, engineers attach metal plates called cold plates directly onto the surface of the GPU or CPU. A coolant, usually water mixed with glycol, circulates through channels inside the cold plate, absorbs heat directly from the chip surface, and carries it away to a heat exchanger outside the building. Liquids transfer heat roughly 30 times more efficiently than air. This means you can push far more computing power into the same physical footprint. The more aggressive approach is immersion cooling. In these systems, the servers themselves are submerged in a tank of dielectric fluid, a liquid that does not conduct electricity, so it will not short out the hardware. The fluid surrounds every component on the board, pulling heat away from every surface simultaneously. Immersion-cooled racks can support power densities above 200 kilowatts. Meta is deploying air-assisted liquid cooling across more than 40 million square feet of its data center footprint. Google has been running liquid-cooled systems at scale for years. All of this heat has to go somewhere. The heat extracted from the chips moves into building-level cooling systems, usually chilled water loops that carry heat to cooling towers on the roof or outside the building. Those cooling towers reject the heat to the atmosphere through evaporation, and evaporation requires water. A lot of water. A large hyperscale data center can use up to 5 million gallons of water every day, the equivalent of a town of 50,000 people. Google reported using more than 5 billion gallons of water across all its facilities in a single year. 2/3 of the new data centers built or in development globally since 2022 are in places already facing water stress, including large portions of Texas and the American Southwest. The engineering of a data center is, in some ways, an engineering problem of water as much as electricity. If you subscribe now, I cover infrastructure and real engineering topics like this every week. There is one more layer of engineering inside these buildings that most people never think about, and it is arguably the one that makes AI specifically so hard to scale. That is the networking layer. Training a large AI model is not something one chip does alone. It requires thousands of chips working together simultaneously, splitting up a massive computational problem, processing their piece, and constantly exchanging results with each other. The speed at which those chips can communicate with each other determines how fast the model trains. The connections between AI chips inside a data center use a technology called InfiniBand, a high-speed networking protocol that can transfer data far faster than standard Ethernet. But there is a physical constraint built into this. The optical cables used to connect GPU-S to the networking switches that coordinate all of this traffic have a practical reach of about 50 meters. Beyond that, you need more expensive hardware, and the latency starts to accumulate in ways that hurt performance. This is why you cannot just spread 30,000 GPU-S across a city and expect them to work as a single system. They have to be in the same building, or a cluster of buildings on the same campus, physically close enough that the cables between them stay short. The networking requirement shapes the physical footprint of the data center as much as the power or cooling requirements do. This is also why building a data center is not like building a warehouse. You cannot just find a cheap piece of land somewhere and drop servers on it. The site has to have fiber running to it. The power has to already be there, or buildable on a short timeline. The water supply has to support cooling, and the facility has to be dense enough that thousands of high-performance chips can communicate with each other at the speed the workload demands. Which brings us back to the grid. US electricity demand was nearly flat for 20 straight years. From roughly 2000 to 2022, consumption barely moved. The country got more efficient. Industrial output shifted. Population grew, but power used did not track it the way analysts expected. That trend broke in 2024. Data center electricity use jumped 17% in 2025 alone, according to the International Energy Agency, far outpacing global electricity demand growth of 3%. The IEA projects that data centers worldwide will consume nearly 950 terawatt-hours of electricity by 2030, more than the total current electricity consumption of Japan. In the United States, data center demand is expected to nearly double between 2025 and 2028, from roughly 80 gigawatts to 150 gigawatts. That is the equivalent of adding a country with Spain's total energy needs in 3 years. The grid was not built for this. Dominion Energy, which serves most of Virginia, is planning to invest $50 billion in new transmission lines, substations, and generation between 2025 and 2029. It has proposed a 14% rate increase for residential customers in 2026, citing data center growth and AI demand as the primary drivers. Virginia Senator Danica Roem, who represents parts of the region, put it plainly while discussing the state's own analysis. Your residential electricity costs will go up because of data centers. Tech companies are responding to the energy constraint in ways that would have seemed extreme 5 years ago. Microsoft, Google, and Amazon have all signed agreements with nuclear power plants, because nuclear is one of the only sources of power dense enough and reliable enough to meet the around-the-clock demand of a hyperscale facility. The pipeline of conditional agreements between data center operators and small modular nuclear reactor projects grew from 25 gigawatts at the end of 2024 to 45 gigawatts by early 2026. 3 Mile Island, the plant famous for the worst nuclear accident in American history, was relicensed and renamed specifically to power Microsoft's data center load. The engineering challenge of building these facilities is remarkable. The engineering challenge of powering them is becoming a national infrastructure question. The next time you use an AI tool, remember that the response arriving in seconds required a building engineered to never stop running, drawing power equivalent to tens of thousands of homes, cooled by millions of gallons of water, networked by cables that cannot stretch beyond the length of a city block. The cloud is not up in the sky. It is in Ashburn, Virginia, sitting behind a chain link fence, and it is hungry for power.